My name is Ryan Marcus. I'm assistant professor at the University of Pennsylvania. Today I'll be presenting BFTBrain, our work applying reinforcement learning to adaptive BFT consensus. Before I start, I have two pieces of bad news. The first piece of bad news is that the lead author of this work was Chenyuan. This was the last chapter of his dissertation. Due to some travel issues, he wasn't able to be here today, so you are getting discount Chenyuan today, which is me. But luckily, Chenyuan has started an awesome new job at City University of Hong Kong. I highly recommend you check out his new lab and all the cool stuff that he's working on. I'm going to do my best to do his work justice here. The second piece of bad news that I want to deliver is that I am an imposter. This is, in fact, my first NSDI. I hope it's not my last. You all have been wonderful hosts and very, very welcoming. But I tend to work in database systems and in machine learning and not in networking. So it's a little unfortunate that I have to present Chenyuan's work, but I'm going to do my best. As a database person, I tend to think of applications as having kind of three different planes, and from watching talks today, I realized that these are not the same planes that you all generally talk about, so I thought it might be good to clarify that first. We generally talk about an application plane being some kind of high-level, concept that's developed, the app layer, where the bank is doing their transactions, et cetera, et cetera. Right below that, we tend to talk about a data plane, which is your database, your SQL functions, your storage, your tables, locks, et cetera. And then finally, we have the network plane or the coordination plane, where distributed consensus is maintained, redundancy is used, et cetera, et cetera. Kind of example application that we might be interested in powering might be something like a bank that wants to transfer $100 from account X to account Y. And of course, they would ask that question in SQL. That query would be sent to the data plane or to the database, which would then begin a transaction. While beginning that transaction, the database would make several calls into the network plane, adding additional state or doing additional state transitions from the underlying finite state machine. For example, the database might issue one request to the network plane to say, hey, lock account X and lock account Y. Then it might issue another request to say, subtract $100 from account X. Then it might issue another request to say, add that $100 to account Y. And then it might issue a final request to say, okay, now unlock both of those accounts. And of course, once the network plane confirms that all of those messages are durable, the database can then report to the application layer, hey, your transaction has committed. Things have worked out. This money has been transferred successfully. If there's a failure at some point in this process, both the network plane and the data plane have to negotiate to either roll back that transaction, fail it completely, or erase its effects. What's very, very nice about this kind of model of an application is your application developers, your people at the bank, get to write their application as if they're just talking to a SQL database. And then, we, the folks in this room, get to think about the problem of these very, very complex applications as just a stream of symbols that lead to transitions in some finite state machine that we want to keep, eventually consistent and replicated across a large number of networks. When we look at how these particular applications work, there's two different levels of fault tolerance from the database point of view that we might want to achieve. The first level of fault tolerance we might want to achieve is crash fault tolerance, where some node in your network may crash, it may lose all of its data, it may become unavailable, there could be a network partition that prevents it from being reachable, et cetera, and we want our application to be able to continue working in this scenario. Another potential model for faults, which you might care about if you're writing a highly secure application, like a bank or something in the military space, is that a node may become adversarial. And in this case, it's not just that the node has crashed or that the node is no longer available, but it's that node might be actively doing things to try to trick you into making a mistake or letting some state that shouldn't be representable suddenly be representable. So in addition to possibly just crashing a node in the Byzantine fault-tolerant model, we also might think our nodes might go a little haywire, might be controlled by an adversarial actor. Now, this community, and I'm very, very thankful for this, has made a ton of really, really, really awesome progress on crash fault tolerance. If we take this bank application and a common benchmark that we use to measure it, and we execute it on kind of today's technology, we'll see that about a third of the time is spent in the application layer, 48% of the time is spent in the database layer, and only 20% of the time is spent in that network layer or network plane, which is really, really awesome. It means that the database people, us, we're the problem. It's now no longer a kind of network networking issue, right? That's not the bottleneck to this application's throughput anymore. However, in the Byzantine fault tolerance case, the performance distribution looks very, very, very different. We run the same application, exact same transactions, exact same processes, et cetera. And now, instead of the application taking up about a third of the time, it's around 6%, the database is around 10%, and almost 85% of the time spent processing all the transactions from this particular application are spent in that network layer doing this adversarially resistant distributed consensus. So we wanted to improve this, and you can't improve this by making the application better or making the database better. You could, but you'd be capped out at 16% potential performance gains. But we wanted to do better than that, and in order to do better than that, you need to attack the bottleneck, the problem, the 84% in this particular chart. So one of the biggest problems that we have to face when we decide, like, okay, we want to have BFT consensus, is we have to choose what algorithms to use. And unfortunately, as far as we can tell, there's no single algorithm that's kind of dominant in all cases. We looked at 3 different scenarios that we found real-world applications to be in, and we evaluated kind of 4 different, well, a bunch, but I'm only going to talk about 4 right now, different BFT consensus protocols in each one of those scenarios. So in our first scenario, which you can kind of think of as the happy path, all nodes in our cluster are alive, we have a relatively small request size at around 4 kilobytes, and there's no kind of active adversarial attack going on. In this case, this particular algorithm called Zizava does a really, really awesome job, gives us 13,000 transactions per second of throughput, which is really, really great. But if we run the same application in a slightly different scenario where all nodes are alive, the request size is slightly smaller, but there's a very clever adversarial attack happening called a proposal stall, where the adversary waits the maximum amount of time possible before saying, okay, I agree to commit this particular transaction, then we see a very, very different setup. All PBFT, Zizava, and cheap BFT all kind of slow down to the maximum extent possible because of the timers they use, and the prime algorithm, which is designed to handle exactly this scenario, ends up doing quite well. It has nearly 4 times the throughput of the other 3 approaches. In the final scenario that we considered, when nodes are actually down, but there isn't an adversarial attack happening on the system, cheap BFT happens to perform very, very well, giving us 12,000 transactions per second, which is 2,000 more transactions per second than any of the other particular protocols were able to give us. So as a database person, I have to think, like, okay, well, which one of these processes should I use, right? Which one of these consensus algorithms do I want to pick in order to power my application and make it go fast? And the problem is, my application doesn't exist in just one of these scenarios at any given time. I might be in scenario 1, 9 to 5 p.m. Monday through Friday, when my messages, are relatively small, they're little transactions, et cetera, but I might be in scenario 2 on weekends where my message request gets much larger because I'm running analytics, I'm running reports, et cetera, and I might find myself in scenario 3 when I'm under attack, right? And our kind of preliminary benchmark here shows that there's not really a one-size-fits-all fault tolerance algorithm that we can use in all of these scenarios, right? Because if our application goes through these 3 phases, there's no one algorithm that's going to give us solid performance all the way through. The second problem is that, at least to me, the number of known BFT algorithms is growing very, very quickly. If you dial the clock back to 1999, there were only around 2 of these algorithms to potentially choose from. Now there are 26 plus of them, right? So more and more algorithms are going to continue to be developed. They're all going to have different performance constraints. We need some way to deal with them in a more structured or more automatic way than what we have today, which is kind of just relying on expert knowledge. So what we really want to do is handle 2 key problems. First, we want to handle the problem if there's a strong affinity between a particular workload in a scenario and a protocol, right? Some protocols work great in some scenarios, some protocols don't work very well in other scenarios. And the second key problem we want to address is that there's an ever-increasing number of protocols that just keep building up and building up and building up. There's some prior work called ADAPT, which took a very interesting approach to this problem, where they pre-computed an optimal mapping between, okay, if I'm in this scenario, then I should choose this protocol. The problem with the optimal mapping approach is that there's a whole lot of different hardware configurations and workloads, and as the number of hardware configurations and workloads increase, the cost of computing this optimal mapping is going to get more and more and more expensive. Similarly, as more BFT protocols are published and come out, you're going to have to recompute this mapping for every single one of those new protocols that comes along. And finally, if you do make this pre-computed mapping, you've essentially created a strategy guide for your adversary, right? If you come up with a pre-computed mapping that says, if we observe this amount of latency or this amount of delay or this amount of nodes down, we're going to switch to protocol X, your adversary now kind of has the guidebook to say, okay, well, I can get them into protocol X by inducing these network conditions, and then I can use my specialized attacks on that particular configuration. So very similar to the mutants work that was presented at the top of this session, we decided to use a reinforcement learning approach that can actively learn and swap between these different protocols at runtime using the actual real measured throughput as a reward. The real motivation for using reinforcement learning is that if there is some adversary who figures out an attack, that attack must necessarily compromise throughput, right? And so any attack that compromises throughput is something we want our system to be able to avoid. We made a couple of assumptions in order to make this happen. The first assumption that we made is that all of our protocols are eventually consistent, fully replicated finite state machines that converge to a linear log, which means that we're not considering the kind of newer DAG protocols that are out there just yet. The second assumption that we make, which is an assumption that a lot of BFT protocols try to build into their systems, is that protocols never fully stall. You know, they might go to 1 transaction per second, they might get really slow, but they always have some kind of liveness property. With these two assumptions, the system that we built is intuitively pretty simple. Essentially, the way that it works is each node has inside of it a learning agent that looks, that every time a certain number of transactions go through, that learning agent kind of looks at the previous state and the previous throughput that was achieved and tries to evaluate whether or not a protocol change is needed. The way that this is done is once that threshold is hit of a certain number of transactions being processed under the existing protocol, the reward and state information are harvested or collected on each node individually. Then each node uses a specialized deterministic reinforcement learning algorithm that's going to select the next state. It's very important for this reinforcement learning algorithm to be deterministic because we need all the learning agents on all of the nodes that are involved in this network to come to the same decision about what state to select next. After that decision is made, and we have a guarantee that all of the agents make the decision to change to the same protocol, all the nodes then agree to switch to that new protocol at some kind of high watermark. So they pick some transaction number in the future, and they say, okay, when we get to track transaction, 10,024, we're all switching from PBFT to cheap BFT. And then when that high watermark value is hit, you switch to using that next protocol. And this is why we need that liveness assumption, because if you're able to fully stop an algorithm from progressing, you'd never hit that change point, and then your system would no longer be live. Now, in order to do this, this is quite tricky to get right. There's kind of 3 really interesting problems that you need to solve. The first problem you need to solve is that you need to ensure that learning is deterministic, even in the presence of adversaries, right? You need every single learning agent, after they do this reinforcement learning thing, to come to the same conclusion about what protocol to switch to. The second interesting thing you need to solve is that you need to ensure that all of the feature values that you collect are accurate even in the presence of adversaries. Right? How is one node supposed to know what the throughput of the entire system is, right? Especially if there's an adversary maybe giving you incorrect information. The third kind of interesting problem is that you have to ensure that switching to a new protocol is seamless and correct, that you don't have any in-process transactions that get kind of messed up by the transition from point 1 to point 2, and you need to make sure that when you do make that transition, you've preserved the correctness of the finite state machine, and you've made sure that it's still replicated and durable and all that very good stuff. In an attempt to get our student Chenyuan as much possible recognition as we can, I'm not going to talk about any of these things, and I'm just going to hopefully refer to our paper where we talk in detail about all 3 of what I think are these very interesting problems. If that's not sufficiently convincing, I want to walk you through some very basic experimental results that we have from BFTBrain. This table shows 4 different scenarios that closely mirror real-world setups that we were able to observe and the performance of a whole bunch of different state-of-the-art linear BFT protocols. Now, I think for the first time at NSDI, I'm very happy to say that in this table, we are not the winner, right? The actual highest throughput protocol in each one of these scenarios is not BFTBrain, right? But BFTBrain gets very, very, very close to this optimal within about 5% of the throughput of each one of these optimals in a pretty short amount of time. So on the far right-hand side of the table, we list the convergence time. This is saying that in about between 1 minute and 6 minutes, BFTBrain is able to achieve performance that's approximately within 5% of that optimal protocol. Right? So while Zizava, cheap BFT, and Prime are optimal in different scenarios, BFTBrain is able to get close to the performance of those methods in a relatively small amount of time. If you don't know what scenario you're going to be in beforehand, or if you're like me and you're not smart enough to read the description of scenario 1 and know that Zizava is the best algorithm that you can possibly use, then BFTBrain finally becomes the winner. If we look at the average across all 4 of these different scenarios, and if we look at the worst case across all 4 of these different scenarios, we can see that BFTBrain gives us the highest throughput over any other single algorithm, because BFTBrain learns to switch between PBFT and Zizava and cheap BFT and Prime, et cetera, in order to maximize throughput as things go on. So if you don't know what kind of environment you're going to be in, BFTBrain is the best choice, both in terms of the average throughput that you're going to be able to achieve and in terms of the worst case throughput you're going to achieve. We tested BFTBrain in a very dynamic environment, just like the banking scenario I described, where attacks start and stop, where packet sizes change quite drastically, where nodes may crash and nodes may come back. And we compared the performance of BFTBrain to the best single fixed protocol that we could find, which was cheap BFT for this particular experiment, and the worst single choice that we could have made, which I believe was Prime, but I'm not 100% sure. And we can see we've written in red the algorithm that BFTBrain is choosing at each point along this particular curve. And we can see that BFTBrain moves through quite a large number of protocols in order to achieve higher throughput than the single best choice, and certainly much higher throughput than the worst single choice. Again, just to reiterate, this was Chenyuan's work. You can check out Chenyuan's awesome new lab at the City University of Hong Kong at his website. You can check out our BFTBrain paper if you want to see our answers to those 3 very interesting questions. And if for some reason you'd like a copy of these slides, you can get that at this URL. That's all I have for you now. Happy to answer a couple questions.